All right, this is lesson 2 of our second unit. Today we're going to be looking at systems of equations. This should be a review topic for most everybody, both in Math 2 and in Math 2 Honors. We do look at systems a little bit, so it should be a review. Shouldn't take too long, and hopefully it will just remind you how to do this and it won't be brand new. So the first thing I just want to talk about is that a solution is just a value or a set of values that makes an equation true. So if we have the equation y equals 2x, there are many solutions that make that true. One solution would be if x is 2, then y is 4. That's true for this equation. Another solution is if x is 5, y is 10. Another solution, if x is -8, y is -16. There's lots and lots and lots of combinations of x and y that make this equation y equals 2x true. And a graph is really just a visual representation of every single possible solution to that equation. So you can see the solution x equals 2, y equals 4 is a point on the graph right here. And the other two solutions that I showed up here, they're not shown on the graph just because it's not a big enough picture, but it would be part of that graph. That's why we show those lines extending, is because there are more solutions that don't even fit on our coordinate plane. But we could always get a larger coordinate plane to show those other solutions. So remember, a graph is just a collection of every single possible solution. So today, as we look at systems of equations, that idea can come in handy. So a system of equation is just a set of two or more equations that use the same variables. And usually you'll see them grouped together with a little brace like this. That's called a brace. So the solution to a system of equations is a value or a set of values that make all of the equations in the system true. So below I have an example and a counterexample. The first one, if x equals 0, y equals 0, that is a solution to the first equation. 0 is equal to the absolute value of 0, but it doesn't work for the second solution. 0 is not equal to 0, the square root of 0 plus 2. So 0, 0 is not a solution to the system because it only works in one of the equations. The other equation it's not true for. The other example here, if x equals -1, y equals 1, well, in the first equation, is it true that 1 is the absolute value of -1? That is definitely true, so it works in the first equation. And if we try it in the second equation, we want to know, is y equal to the square root of -1 plus 2? And that's also true. So the solution, x equals -1, y equals 1, it works for both of equations, so it is a solution to the system. Now we're going to focus primarily on graphing these systems of equations. When we graph systems of equations, again, we're still just looking for a solution that is true for both of the equations in the system. And so if you think about that the graph of the absolute value of x, this first part, I'll graph it in blue, it starts at the origin. If we collect every single point for which that equation is true, it creates this graph of an absolute value. And that represents every single point for which y is equal to the absolute value of x. For the second equation in our system, y equals the square root of x plus 2, that's a square root equation. It starts at the point -2, 0. We can use our up 1 over 1, up 1 over 3, up 1 over 5 pattern, 1, 2, 3, 4, 5. And we get this shape. That green shape is this collection of every single possible point for which y is equal to the square root of x plus 2. So if we are looking for a point that's true for both of these equations, we are looking for essentially the intersection of those two equations. or those two graphs. So we have two solutions in this case because it intersects twice. Wow, I can write. Two solutions. In this case, we have a solution x equals -1, y equals 1. So that's this first point on the left, and our other solution is if x equals 2, y equals 2 as well. So we have both of these solutions. Now, sometimes people like to write these as points. So you would write the point -1, 1 and the point 2, 2. I'm fine with that. It's sort of understood that that's an x and a y. So if you want to write your solutions as points, that is fine. Okay, well, sometimes the solutions aren't at a nice point, or sometimes we're dealing with equations that are more complicated and we want to use our graphing calculator to help us graph them. And in that case, we can use the graphing calculator to help us find that intersection point. So I'm going to switch over to my graphing calculator. Last time we practiced graphing these, or not these, but we practice graphing things in the graphing calculator, and today we're going to do that as well. So in your graphing calculator, or if you have an app on your phone that you use to help you graph these, that's fine at home. Or if you're at home, you can also use the website desmos.com to help you graph these things. If you hit the y equals button, you have the place where you can enter in functions that you want to graph. Again, that was y equals. So the first one that we want to graph is the square root of x. I'm going to go out of the square root, and then we want to add 1. And then you can go ahead and just put in the other equation as well. X squared minus 2x minus 2 is our next equation. So once you have them both typed in, if you hit graph, the calculator will graph them both on that same coordinate grid. And you can see the square root graph and the parabola are both there. Now you can see that the intersection point is right here. But if we want to know exactly where that intersection point is, we can find that from the calculator. On your calculator, you'll hit second, and then the calc up above trace is what we want to do. We practiced using this button last time when we were doing mins and maxes, and you can see below maximum choice number 5 is the intersection or intersect. So I'm going to choose choice 5. When you do that, your calculator wants a little bit of information about which intersection you're looking for. Now, it's maybe obvious to us as we look at this that there's only one intersection here, but sometimes it's potentially you'll have more than one intersection, or you may have 3 graphs shown. So the calculator just wants you to sort of clarify a little bit. It's going to ask you first curve, and you just need to make sure that your cursor is somewhere on your first curve, which is the square root. Hit enter, and the next question it asks you is second curve. Now it should have moved itself down to that second curve, if you can see it there blinking, and it moved itself. If it didn't, you can go up or down to move to the right function, and it's on my parabola now, so I hit enter. And then finally, it always wants you to make a little guess. It just helps it get closer to it helps it to be faster and get closer to the solution. Whoops, overshot it. So you move your little cursor sort of close to that intersection. It doesn't have to be right on it, but get it close. And once you do that, it can calculate that intersection pretty quickly. And so it's not a nice point, so to speak. It's at 3.418451 for the x, and for the y, 2.8489054. So it could be anywhere that it crosses, and in this case, that is our intersection. So here's the graph. This is what it told us. So maybe we could round to, I don't know, 2 decimals, 3.42 and 2.85 is our intersection here. So oftentimes people want to know, why do we have to study this in math? Systems are kind of interesting from the perspective of business and economics. Businesses sometimes think about their revenue, that's the money that they bring in, and their cost, that's what it costs them to operate. And if you think about that intersection point, that's essentially their break-even point. If they operate to the right of that point, they're running a profit, and if they operate to the left of that point, they're running a loss. This next graph also shows their break-even point. The total revenue is shown in blue, and the cost is shown in red. In economics, they talk about things like marginal cost and marginal revenue, which are a little bit different than profit and cost or revenue and cost. But again, they look for that they look for that intersection point when they're studying these models. And that point is where they get their maximum possible profit. So now you know. Okay, so just as you're looking at these systems, keep in mind that the number of solutions just depends on the system. It's possible that the two equations will not have an intersection, and if that's the case, that's no solution. It's possible that they just have one intersection point, and then there would just be that one solution you would list. In the right situation, there could be multiple. That's funny, it's backwards. There could be multiple intersection points. This one happens to have 4 points of intersection. So there would be 1, 2, 3, 4 solutions to this system. And in this case, you would have to either estimate those by looking at the graph or use the graphing calculator to get the exact solution. And then one last final case is kind of interesting. The system is shown here on the equations, and the graph, the dark blue is the graph of the top equation, and the bottom equation is shown in the dashed light blue. And you can see that when you graph those two equations together, they actually are the same thing. They algebraically look like they're different, but they are equivalent. So when you graph them, they're the same. And if that's the case, if they are right on top of each other, so to speak, that means that there are infinite solutions. Every single point on that dark blue line is also a point on that light blue line. Okay, so we're just going to practice a couple of these. Our first system, the first equation in this system, I'll graph in blue. It is a straight line. It has a y-intercept of -5, and the slope is 2, so up 2 over 1 for the slope. Something like this. Second equation I will graph in green. So it's a square root graph. It starts at the point 1, 1, and it has a stretch of -2. So from that point 1, 1, I'm going to go down 2 over 1, down 2 over 3, down 2 over 5. And there is my square root graph. So the solution to this system, looking for that intersection point, it would be x equals 2, y equals -1. Or if you like, you can write it as the point 2, -1. Recently, in the last unit on radicals, we would actually use this idea for solving equations. And when we're using the idea of systems to help us solve an equation, keep in mind it was not a system to start with. We introduced that idea of a system. So when we come up with a solution here, our equation originally only has x's. We are looking for an x answer. We are not interested in the y per se. Really, the x is what we're after. So if I graph these, I'm going to graph the first one in blue. It's a cube root. Start graphing it at the point 3, 4. And the cube root pattern, up 1 over 1, up 1 over 7. down 1, back 1, down 1, back 7. So we can't fit a lot of that cube root on there, but enough. The second part of this is a straight line. It has a y-intercept at -7, and the slope is 3. So we go up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1. There's our straight line. So again, here is our intersection point. The intersection happens at the point 4, 5, but for our equation, we are really only interested in the x, so we would report our answer as x equals 4. Here was a practice one for you to try. I'll go ahead and graph it. So if we treat this as a system, we're going to graph this parabola first. So it starts at the point 3, 7, and it has a negative coefficient there, so it is reflected down. 1, 3, 5. Kind of missed a little bit. So that was the first part of this system. Again, we're treating it as a system. And the second part is this square root. It starts at the point 1, 9 up here, and it's stretched by a factor of -3. So down 3 over 1, down 3 over 3, down 3 over 5. And there's our square root. So you can see that we have 2 intersection points, and that those points are our 2 solutions. Again, our equation only had x's in it to start with. We introduced the idea of using a system to help us solve it. So we are only interested in the x values of the solution. So we get the 2 solutions, x equal 2 and x is equal to 5. Okay, one last concept. Sometimes instead of having 2 equations, we have a system that is given to us with different representations. So in this case, this example on the board has a linear function, f of x, shown in a table, and we have a function g of x, which we are given the graph of. It happens to be an exponential equation. So number 1, look at what it's asking you. For which x value, so we're looking for an x value, for which x value are the 2 functions the same? Now you could try comparing the graph and comparing the table and thinking about it this way, but I think one of the fastest and most efficient ways to solve a problem like this is to graph it and look at those 2 graphs together. Now g of x is already graphed, so we just need to graph f of x. I'm going to graph it in green. So the first point, -6, 8, is here. -4, 7 is the next point on our list. 0, 5 is the next point. 4, 3, and 6, 2. So if we graph these points, you can see that line forming. And this is what that line looks like. So now that you have that line graphed with g of x, it's pretty simple to answer the question, for which x value are the 2 functions the same? Well, they're the same for the x value 2. Our solution is x equals 2. Again, since it's specified x value, I don't really need to list, and I really shouldn't list the y value that goes with that. One more, and then I think this is the end. So we want to find a solution to the system. If it just says solution to the system, you do want the x and the y, so you can list the points if you like. Find the solution to the system given the different representations. So this tells me f of x is a quadratic function, and for g of x, it gives me the equation, and sometimes that's called the symbolic representation. And the easiest way to solve this, again, is to just graph them both and look for their intersection. I'm going to graph f of x, the quadratic, in green. So let's plot those points. Negative 3, negative 2, negative 2, negative 3, negative 1, negative 2, and 0, 1. And as you look at those 4 points, I hope you can see that it's a parabola. It told me it was a quadratic. So if you remembered that word quadratic means that it's a parabola, that's good. If not, hopefully seeing those 4 points reminded you. So we've got our parabola here. And g of x I will graph in blue. So we've got an absolute value. It has a vertex, at negative 2, negative 3. Sorry, positive 3. I can speak. Negative 2, positive 3 for the vertex, and it has a negative coefficient, so that means it's going to open down with the slope of 1. So we have two solutions. Our system has two solutions, 2 points of intersection. So our first solution is negative 4, 1, and our second solution is the point 0, 1. And that is it. So that was lesson 2. The homework assignment, if you don't have it, is posted on my website. If you do have it in your packet, it is the salmon colored one that's kind of orangish. That's it.